This is chapter 12 from Master Math Mentor's AP Calculus AB manual. We're going to be going over it today in detail. This is derivatives of transcendental functions. We're talking about functions not like x squared or square root of x, but we're talking about things like trig functions like sine x or natural log of x. Specifically today, natural log of x and e to the x. The derivative of natural log x, we're going to explore what this is by looking at the table. We're going to build a table for the derivative using our calculator. So I know you can't see my calculator at the moment, but if you'll hit the y equals button on the top left, y equals on the top left, and then you'll hit math, you'll go down to number 8 in derive. And inside the parentheses, you'll type ln x. ln is on the left-hand side, the third button from the bottom. You'll close that parentheses because that parentheses was open, so you need to close it. And then you'll type x equals x. And then we'll go look at our table. I want my table to auto-generate these numbers for me. And I've already set my table set up to do that. If you notice, you look at numbers like -4, -3, -2, -1, 0. On your table, those all say error. And why do they say error? Let's talk about this idea of natural log. Natural log of x is this idea of log base e of x. And whatever that is equal to is really the exponent. So this idea would be like e to what power is equal to the x value. So in this case, if we were looking at negative values for x, like e to what power is equal to -3, well, that's actually not possible because you can't raise a positive number to a power and get a negative number. That's never going to be possible. So ln natural log is actually undefined for any values of less than 0. So it's only defined for values greater than 0. All right, so looking at the table, I have it pulled up on my calculator here. ln of 0 does not exist according to my calculator. ln of 1 is 1. ln of 2 is 0.5. ln of 3 is 0.3 repeating. ln of 4 is 0.25. ln of 5 is 0.2. ln of 6 is 0.16 repeating. ln of 7 is 0.1429. ln of 8 is 0.125. ln of 9 is 0.1 repeating. And ln of 10 is 0.1. So by looking at this, we should be able to see that the derivative, like 0.5, would be 1/2. 0.3 would be 1/3. 0.4 would, or 1/4 would be 0.25. 1/5 would be 0.2. So we should be able to see the relationship between the value of x and the value of the derivative, and that relationship is 1/x. So the derivative of ln x is actually 1/x, and we see that here in this first box. The derivative of ln of x is 1/x. Notice x has to be greater than or greater than 0. Can't equal 0. The reason it can't equal 0 is because we can't divide by 0. Can't divide by 0. All right, this second part here, we have ln of u being some function of x. So what we're going to do, we're going to let chain rule here. We're going to take the derivative of ln of something, which is 1/something, whatever that something is. We're going to leave it by it like it is, and then we're going to multiply that by the derivative of what that something is. So this is just notation here for chain rule. It looks kind of confusing, but really just notation. And if we had absolute value, ln of absolute value of u, we're going to take 1/u. Again, that's just the derivative of the natural log part. Natural log of something is 1/u, and chain rule says we have to multiply it by that something. Looking at this notation, u prime over u, that's just another way of saying Really, this idea, it's going to be 1 over u times the derivative of u, and we can just write that as u prime over u. Alrighty, let's hop right into some examples. ln of 4x, we're going to take the derivative of the natural log first. This 4x is going to stay the same, so 1 over u, whatever u is. In this case, u is 4x. We're going to multiply that by the derivative of 4x. Derivative of 4x is 4, and the 4's canceled out, and we get derivative of natural log of 4x, 1 over x. Natural log of x squared over 3. I'm going to try to start writing these the way they wrote them earlier with the u prime over u. So this would be our u. So u would be x squared minus 3. Derivative of natural log of something is 1 over that something times the derivative of that something. The derivative of that something in this case, just 2x. Instead of writing it as two fractions being multiplied together. Alrighty, number 3, y prime is going to be equal to 1 over something. That something is going to be 3x squared minus 5x plus 8. And then we're going to multiply that by the derivative of this inside piece, 3x squared minus 5x plus 8. The derivative of that would be 6x minus 5. And we roll on to number 4. All right, number 4, we can rewrite this as natural log of x to the 1/2 power. The x is the only thing being raised to the 1/2 power. So we end up with y prime being 1 over x to the 1/2 power. 1 over whatever that something is times the derivative of that something would be 1/2 x to the negative 1/2 power. We want to clean that up a little bit. We get 1 over x to the 1/2 times 1 over 2x to the 1/2. When we multiply these x to the 1/2s together, x to the 1/2 times x to the 1/2 is x to the first. So we end up with 1 over 2x to the first power. Alrighty, at this point, we have 5 different forms. We can add trig form from chapter 10. We can add ln now from chapter 12. So we still have power product quotient rule from chapter 8. Those are from chapter 8, trig from chapter 10. And now we can add this ln form from chapter 11. As we've seen before, just because it has an ln in the problem doesn't mean we're using the ln rule initially. We probably still would use it later on. Looking at number 5 is a product. So we're going to start with product rule. F prime g plus g prime f. Derivative of x squared is 2x. The ln x stays the same. Plus the derivative of ln x is just 1 over x times f, which is just x squared. We can simplify the x squared over x. X squared over x is just x. One factor of x canceling out. So we get 2x ln of x plus x. If we wanted, we could factor an x out, I guess. And we get 2 ln x plus 1. But that doesn't really serve us a ton there. Number 6 looks like a quotient. We could possibly rewrite this as x to the negative 1 ln x. And then we wouldn't have to use quotient rule, but I'm just going to use quotient rule. We're looking at low d high minus high d low all over low squared. All right, the low is x times the derivative of ln x is 1 over x minus the top ln x times the derivative of the bottom is 1 all over x quantity squared. These x's will cancel out, so we get 1 minus ln x on top all over x squared in the denominator. Rock on. Number 7. Number 7 is quotient rule again. Low d high minus high d low all over low squared. So y prime, our low, is ln x times derivative of x is 1 minus the top x times the derivative of ln x is 1 over x all over x squared. Again, the x's are going to cancel out. So this is very similar to the problem before, but it's just the ln x comes first. Number 8, this would actually be power rule because we have something raised to a power. To take that derivative, we're going to take the derivative of that something raised to the power, which is 5, times that something raised to the fourth power. But then we got to multiply it by the derivative of the ln of x, and that's 1 over x. So we get 5 ln x raised to the fourth power all over x. And we are done with number 8. All righty, rolling on to the next page. We're on page 59 now. All right, this is y equals square root of ln x. We can write that as ln x, the entire thing, raised to the 1/2 power. So this would be power rule in this case. Take the derivative, we're going to do 1/2 times something raised to the negative 1/2. That something doesn't change. That something is ln x. And then we multiply by the derivative of that something, which would be 1 over x. We can move the ln x to the negative 1/2 to the denominator. We can multiply the 2 and the x together. So we get 1 over 2x ln x, and that ln x is raised to the 1/2 power. We could switch that to a square root if we chose. Number 10 would actually be a trig rule. So let's think back to chapter 10. What's the derivative of cosine? We got sine, cosine, negative sine, negative cosine. So derivative of cosine would be negative sine. So y prime is negative sine ln x times the derivative of ln x, which is 1 over x. So hopefully we can just go ahead and write that as x in the denominator. All right, number 11 is actually our ln rule. So we're going to take derivative of natural log first. Derivative of natural log is 1 over whatever's on the inside. So cosine x would go on the bottom times the derivative of that cosine x. And derivative of cosine x is negative sine x. If you remember your trig rules from pre-cal, sine over cosine is tangent. So we get negative tangent x for number 11. Number 12, we got ln of ln x. So this is our ln rule. So we're going to take the derivative of this ln on the outside first. So it's going to be 1 over whatever's inside the parentheses, ln x, times the derivative of the inside. Derivative of ln x is 1 over x. So we get 1 over x ln x. We typically write the x in front. What we cannot do is multiply those two x's together. Log rules that we learned in pre-cal course can really simplify the process for us taking these derivatives. So ln of a times b is equal to ln of a plus ln of b. So if we have a product inside the parentheses, we can break that apart into a sum. If we have a quotient, we can break that apart into a difference. We can actually subtract those. And these properties are going to help us simplify the original problem before we actually take the derivative. And our third property here says that this exponent can actually be written in front of the natural log. So we get b times natural log of a. So if you haven't seen these, you need to familiarize yourself with these and be able to use them to manipulate our function from the beginning before we actually start taking derivatives, because it's going to make our life a lot easier. As you'll see, I'm going to do the first one with the direct approach, and after that, I'm probably just going to use the log rules. So in this case, we got ln x sine x. We're going to take derivative first, and that's ln rule. If we do the direct approach, not trying to simplify that any. So y prime is going to be equal to derivative of natural log of something is 1 over that something. And then we're going to have to multiply that by the derivative of this x sine x piece. And the derivative of that is going to be product rule. So then we're looking at f prime g plus g prime f. So derivative of f would be 1 times sine x plus derivative of sine x would be cosine x times f would be x. So on top of our fraction, we can put sine x plus, we typically put this x in front of the cosine, x cosine x. That way we don't get the two x's mixed up. and multiply them by mistake, divide it by x sine x. So while that wasn't really that complicated, if we use the log rules, it's actually going to be much, much easier. So log rule says ln of a times b is equal to ln of a plus ln of b. So we can use that property right now. And that's going to make taking the derivative much easier. We're not going to have to use chain rule or product rule nearly as often. So this is equivalent to ln of x plus ln of sine x. Derivative of ln x is just 1 over x, so y prime would be equal to 1 over x. Derivative of ln of sine x would be 1 over sine x times derivative of sine x would be cosine x. So we get 1 over x plus cosine x over sine x. So that would be 1 over x plus cotangent x. While our answer doesn't look like that, we can certainly make it look like that if we were to break this into two fractions. We get sine x over x sine x. The sine x's cancel, plus x cosine x over x sine x. The x's cancel. So our first fraction is equivalent to 1 over x. And our second fraction is cosine over sine, which is cotangent. So we do see that we got the same answer. Using log rules was actually much more simple in that case. So we're going to use log rules for the rest of this instructional video. If you want to see the direct approach, I can show you that, but not recommended that you take that approach. Number 14, we can rewrite this ln of x squared plus 2x, and that is being raised to the 1/2 power. There's a property of our logs that says if we have this part of the log being raised to a power, it's equivalent to multiplying by that in front. So this is actually equal to 1/2 times ln of x squared plus 2x. And now taking the derivative, using those log rules, by rearranging it that way, it's going to be much easier than the direct approach. So y prime is going to be 1 over 2. Derivative of natural log is 1 over something, so that x squared plus 2x gets moved to the denominator. I'm not going to multiply that out. And then we're going to take the derivative of the x squared plus 2x. Derivative of x squared plus 2x is 2x plus 2. We can factor a 2 out of the 2x plus 2. So we get 2 times x plus 2 all over 2 times x squared plus 2x. We can cancel the 2's out. So our simplified derivative would be x plus 2 over x squared plus 2x. Much easier to do than the direct approach had we not used those properties of logs. All right, again, we're going to use those properties of logs. This is equal to the natural log of x squared minus the natural log of 3x minus 2. Since this x is being squared, we can also move it in front. So we get 2 natural log of x minus natural log of 3x minus 2. So now to take the derivative, going to be much easier than using ln and quotient rule and all that we would need originally had we not used the properties of logs here. So we get 2 times the derivative of natural log of x is just 1 over x. So 2 times 1 over x is just 2 over x, minus derivative of natural log of 3x minus 2 is going to be 1 over 3x minus 2 times the derivative of 3x minus 2, which is just 3. So that was way easier than trying the direct approach, which we would have had to do just to show you. It would have been 1 over x squared over 3x minus 2, 3x minus 2, and then we would have had to multiply that by a quotient rule, and then we would have had to do a whole bunch of simplifying, and we don't really want to do that. Number 16, using log rules again. We're only going to use log rules this time. This is ln x squared minus 1 over x squared plus 1 raised to the 1/2 power. So we can move the 1/2 in front. And at the same time, I'm going to go ahead and rewrite this as a it is a quotient, so I'm going to go ahead and rewrite this as subtraction x squared minus 1 minus ln of x squared plus 1. And notice I've left the 1/2 out front. Otherwise, both of these here would have had to have the 1/2. So we're just going to leave the 1/2 out front when we take the derivative. Derivative of natural log of x squared minus 1 is just 1 over x squared minus 1 times the derivative of that. So we can go ahead and put that in the numerator. Derivative of x squared minus 1 is just 2x minus 1 over derivative of natural log of x squared plus 1. Derivative of that is 1 over x squared plus 1. And derivative of x squared plus 1 is 2x. And we can be done there. We could probably just leave it like that. We could try to find like terms if we wanted to. We could probably distribute this 1/2 out to make it look a little bit better. And the 1/2 is actually going to cancel with the 2's. So we get x over x squared minus 1 minus x over x squared plus 1. There's not much else we can do with that. We could combine like terms by making common denominator, but really not necessary. All right, we could also use implicit differentiation from chapter 11 with natural logs. Derivative of x squared would be 2x dx dx, just to review, but we don't have to write the dx dx because it's just 1 minus 3 times the derivative of natural log of y is 1 over y. So we multiplied that by 3, so I'm going to put the y in the bottom. dy dx plus derivative of y squared would be 2y dy dx. And derivative of 25 is 0. And we're solving for dy dx. So anything that doesn't have a dy dx, we're going to move to the other side. So we're going to subtract 2x from both sides. Cancels here. We get negative 3 over y. Negative 3 over y dy dx plus 2y dy dx is equal to negative 2x. All right, now a little algebraic trick that we're going to do here is we're going to multiply everything, the entire equation, by y, and we're going to do that so we can cancel this y in the denominator. So when we distribute it to that first fraction, the y cancels, but we have to distribute it to everything after that as well. So we end up with negative 3 dy dx plus 2y squared dy dx is equal to negative 2xy. Now, on the left side of the equal sign here, we have 2 dy dx's that can't be combined into like terms, but we can, another little algebraic technique we can use, we can actually factor that dy dx out. And that's what we want to do in this case. Once we factor the dy dx out, we're left with negative 3 plus 2y squared. And now that we factored it out, we can actually divide everything by that negative 3 plus 2y squared on both sides. And we end up with our final answer. Dy dx is equivalent to negative 2xy on top, and in the denominator, negative 3 plus 2y squared. Another variation of this answer, we could factor the negative out of the denominator. And if we factor that negative out of the denominator, we get negative parentheses 3 minus 2y squared. And then these two negatives actually cancel each other out. So we're left with 2xy over 3 minus 2y squared. So that would be an equivalent expression. And sometimes the way you solve an equation, your signs might be off by a negative, but we can factor that negative out to make the signs match. All right, sometimes we are asked to find the equation of a tangent line. Remember, equation of tangent line, y minus y1 equals the slope times x minus x1. So a couple things we need. We need x1, and y1. We already have that. So in this case, we need the slope of the tangent line. And we're going to find that by finding f prime of 1. So looking at the derivative, y prime, derivative of 4x squared is 8x. Derivative of natural log of 2x squared minus 1 is 1 over something times the derivative of that. Derivative of 2x squared is 4x. Derivative of negative 1 is just 0. So we're going to plug 1 into that expression to figure out what our slope of our tangent line is 8 times 1 minus 4 times 1 all over 2 times 1 squared minus 1. Doing a little bit of computation, we get 8 minus, that's going to be 4 on top, and 2 minus 1 is 1 on bottom, and 8 minus 4 is 4. So we get the slope for our tangent line is equal to 4. So the equation of our tangent line would be y minus this value, 4, is equal to m, which is the slope we just found, 4 times x minus the x value, which is 1. And we can clean that up a little bit, probably solve for y if we wanted to get y on one side by itself. So we get y minus 4, distribute the 4, we get 4x minus 4, and we add 4 to both sides, and it looks like the 4's cancel out, and we get y equals 4x. Again, this is used from Master Math Mentor, his AP Calculus AB exam manual. We use that in our class, and I am using all of his examples with permission. In the next video, we will take the derivative of exponential e to the x.